Well, as you can see, we're going to try a little new feature here today. I don't know how you guys have been doing, but being at home, confined mostly to my home office, one of the first things to go has been personal hygiene. So, shaving, getting dressed, things like that. So I thought, well, if I put myself in the videos, that'll force me to at least practice some good personal hygiene and prevent me from doing things like the other day I parted my hair in the middle like I had back in high school, back in the early 1980s. And after finding it somewhat amusing, my wife quickly informed me that she never really wanted to see that again. So anyway, try to practice some good personal hygiene. So see how this goes. But in any case, we're going to start a totally new topic, which is going to take up a fair amount of the rest of the semester. So we finished up optimization in the last video, and you're working on problem set 6 on that. And so now for the next 3 chapters, we're going to be discussing solving differential equations. So we'll do some of the background work in chapter 7, talking about how we discretize the differential equations and approximate the derivatives. And then we'll look at boundary value problems and initial value problems in the next 2 chapters. And again, that'll take us some time towards the end of the semester. So I want to start by introducing differential equations. You've seen differential equations in various settings and various classes. You had a class on differential equations, Math 252. And so I just want to introduce differential equations and remind you how important they are. Hopefully you already realize this, and it is fun. For me, this is really when math became, I could see the connection between the math and the physics of reality. And that's when things really get interesting. So many of the governing principles that our systems are subject to, such as conservation of mass, momentum, and energy, when we actually formulate the governing equations for these various principles, they end up being ordinary and partial differential equations. So they're all over the place in our engineering applications. And then calculus, essentially you can think of as the mathematics of change. So slopes are the rate of change of a function and so on. So calculus is the mathematics of change. And then differential equations govern that change. And it could be a change in time, which we say temporally, or in space, spatially. And the systems could be any type of system. It could be mechanical, electrical, chemical, biological, whatever the case might be. So let's just walk through some examples throughout mechanical and aerospace engineering where you have or you will see differential equations coming up. So dynamics, so of course like MMAE 305. So basically the governing principle there is conservation of momentum in the form of Newton's second law, F equals ma. And you'll remember we applied this to our spring mass example early on in the semester. And we got these 2 coupled second order ordinary differential equations for the spring mass system. So essentially, again, dynamics is Newton's second law applied to all kinds of crazy systems. In mechanics of solids, so MMAE 202, you come across a number of different examples. Here's one, the beam deflection equation. So the E times the I, those are properties of the material that the beam is made out of, as well as the shape of the beam. And then P is the load on the beam. And then V is the deflection as a function of x across the length of the beam. And so this is a 4th order ordinary differential equation for that deflection. In fluid mechanics, so MMAE 313, we have conservation of mass and conservation of momentum. We call these the Navier-Stokes equations. They're written here in vector form. So V here is the velocity, so del dot V, that's the divergence of the velocity field. If it's incompressible, then that is 0. And then here's the corresponding conservation of momentum equation. And essentially it's just F equals ma again. So the F is actually on the right-hand side. So the sum of the forces, you have pressure forces, and you have viscous forces. So forces because of friction between fluid particles. So whatever forces you have, you could have buoyancy forces on there as well. And then on the right is the mass in the form of the density times the acceleration, which is now looks more difficult than just a or the rate of change of velocity with respect to time. We have this additional term which you'll learn about in 313 why that is the case. But this is essentially convection, so the fluid particles are being convected around by the velocity field v, and that gives rise to the acceleration term on the left. Heat transfer looks quite similar. This is conservation of energy, so you can see the conservation of mass, momentum, and energy. In conduction, where nothing is moving then except the heat itself, then partial t partial little t is alpha del squared t. So the del squared, you can see that here as well. This is what's called the Laplacian, and that represents diffusion of something. So diffusion of heat, diffusion of momentum, diffusion of species, diffusion of virus, whatever. And then we have convection of that thing. Now, in a conduction setting, there is no convection, but in a convection setting, there is. So you can see these two equations are the same, except that the convection form of heat transfer includes the convection, so the movement of the heat because the fluid particles are actually moving, whereas in the conduction context there is no convection, only diffusion of the heat. And I'll just show you one more example here apropos to the current crisis. I've been looking for a good model to play with for these virus, and this is the best one I've found. You can see up here the URL, and if anybody's interested I can email it to you, but it shows, here's the actual equations right here. So these are differential equations for the growth and decay of disease, and you can see a bunch of different parameters up here that go into those equations, and you can set them. You just slide. So for example, you may hear about this R naught, which is if I were to be infected, on average how many other people will I infect, and so that's a huge determiner in how fast these things, the exponential growth rate that these things grow throughout a population. And their best guess right now is it's about 2, it's between 2 and 3. But you can see the effect of choosing different in real time. You can see the effect of different values of R naught, transmission times, mortality statistics, recovery times. And then it plots the number of people that have been exposed, which is the brown, infected, which is the red, and then hospitalized, that's the light blue, and then the number of fatalities is the dark blue. And you can see how, so this is one of the things that's really interesting to see, is even after the number of cases has peaked, so you can see how each lags the other. So the number of cases peaks here, but then it's some time before the number of people exposed peaks here, and then, but the peak in the number of actual infections peaks later, and then the number of hospitalizations peaks even later, and the number of deaths peaks quite a bit later. So just because you reach the maximum in this curve doesn't mean you're out of the woods in terms of fatalities. So anyway, it's very interesting, and you can see, like I said, you can play with different rates in these equations and just these little sliders and see how much difference it makes. All right, so it's back to so the way we classify these equations, I'll give you 3 of the main classifications of differential equations. They're either ordinary, and basically every differential equation is one or the other of each of these 3 pairings. So it's either an ordinary or partial differential equation, ODE or PDE. This distinction isn't actually terribly important. There's nothing fundamentally different about them. It's just ODEs only have one independent variable, usually x or t, whereas PDEs have more than one independent variable, and that's really the only distinction. And so we use D for ordinary and partial for partial differential equations, but again, there's nothing fundamentally different from a mathematical point of view. A more important classification is whether it's a boundary value problem or an initial value problem. So we call them BVPs and IVPs. So boundary value problems mathematically have a fixed domain, usually in space, like in X. And you have boundary conditions, so you know the behavior at the 2 boundaries, therefore boundary value problems, of the domain. And then you solve for the solution in the interior. Initial value problems are usually in time, so you start at t is equal to 0, and you move forward in time. So usually boundary value problems physically are steady, time invariant, so nothing's changing with time, whereas initial value problems are typically unsteady or time dependent problems. So for example, if you go back to the heat transfer context here, on the left side you'll see these time derivatives. So if they're unsteady, you have to, temperature, capital T, is changing with time, so you have to include those terms, and therefore it's an initial value problem changing in time. If it's steady, so the temperature does not change with time, then those terms go away, and you have the steady form of heat conduction or convection, which, for example, for conduction is just the Laplace equation, del squared T is equal to 0. Now, in that case, it's a boundary value problem. So that's a very important distinction, and in fact, so important that that's how we'll designate different differential equations in the next two chapters. And then another important one is linear versus nonlinear. So a linear equation, differential equation, means everything is linear. So the initial conditions are linear, the boundary conditions are linear, the governing equations themselves are linear, everything is linear. If any one of those things is not linear, so nonlinear, then we say it's a nonlinear system. And I'll show you in the next few videos some of the consequences and behaviors that you can see in nonlinear systems versus linear systems. It turns out that in these epidemiology models, these are actually they are linear models. They are quite complicated. There's a lot of stuff going on in there, but they're actually linear models. Okay, so what we need to realize is differential equations are everywhere in engineering and in physics and in chemistry and biology and so on, and the vast majority of them cannot be solved using the techniques that you learned in Math 252. So in Math 252 you learn various techniques for getting exact solutions we call them closed form solutions, and there's very, very few situations where real equations that govern real physics and real engineering systems, that they can be solved analytically or exactly in that way. So numerical methods really become an essential tool for us, and more often than not, when we're solving differential equations, whether it's in a research setting or an industrial setting, they're normally being solved numerically. So that means they're approximate solutions, but that's the price you have to pay for getting solutions to these more complex situations than you can get analytically. Now we still need to understand those analytical methods. We still need to be able to apply them when they do apply, but more often than not, we're going to have to resort to numerical methods, as we'll discuss here. And so therefore, one of the central goals of computational mechanics is to develop these methods for solving differential equations numerically. And then by doing so, it's really going to open up the full spectrum of ODEs and PDEs. There's essentially no equation that we can't solve using these techniques. It might be hard, it might require massive supercomputing systems, but we can solve it. Good to see Mike email me. Guess I should put on Do Not Disturb, huh? Okay. So again, the price we'll pay for this is that the solutions will be approximate, but the techniques are adaptable to both ordinary and partial differential equations, both initial and boundary value problems. There will be some differences, and that's why we'll look at initial and boundary value problems separately, because they are fundamentally different types of problems. But the fundamentals that we'll look at in this chapter are common to both. So before we get into the hows, so how we actually do these numerical solutions and how we formulate them and actually program and solve them, what I want to do is go through 3 examples of some of my favorite ODEs. So these are relatively simple ODEs. Let's see, one of them is actually linear, the other 2 are nonlinear. These can be solved using Mathematica, using the techniques that we're developing in this course. So I'm not talking about wacky, crazy PDEs that have to be solved on supercomputers. So I'm going to go through these 3 of my favorite ODEs, and we'll just again get a feel for what kinds of physical behaviors we can and must be able to treat, and also the kinds of solutions, more interestingly, the kinds of solutions that these equations lead to. So in this video, we're going to look at the forced pendulum. So you know what a pendulum is. It just has a pivot point at the top and then can wibble wobble back and forth like so. So it has a length L, has a mass M at the end, and has the pivot point. And then when it's hanging straight down, that would be theta is equal to 0, or, and you'll see I'm using U here, and that's because theta will either be 0 or pi, as you'll see. So normally we think of a pendulum like this hanging straight down, but we'll also look at what happens when it's sticking straight up. And the Mathieu's equation that we're looking at here at the top actually governs the stability of a forced pendulum. So by forced, I mean, so you have the pendulum wobbling back and forth again, like before, but now the pivot point is going to be forced up and down with a prescribed trajectory. So it's A cosine omega t. So omega is the frequency that the top is being forced up and down, and A is the amplitude. So big amplitude, small amplitude, low frequency, high frequency. So it's just a regular pendulum, but now it's being forced up and down with that forcing. And so this is, again, this is the equation that you get if you look at the stability of such a forced pendulum. Now the U, the reason why I'm using U here instead of theta, so theta is equal to 0, we call that an equilibrium point, because if you just let a pendulum go, it could stay there for all time. But this is also an equilibrium point, so that's theta is equal to pi, sticking straight up. Now, as you would guess intuitively, this one is stable, because if I disturb it, it's just going to wibble wobble back and forth, but the amplitude is going to stay confined to small amplitudes around 0. This is an equilibrium point as well. If I could get it just right, perfectly vertical, and then leave it for all time undisturbed, it will stay sticking straight up. But if you disturb it a bit, of course it's going to fall down, so it's unstable. So this equation, the Mathieu's equation, actually allows us to look at what happens to the pendulum because of the forcing. So again, regular pendulum with the forcing. Okay, so again, theta is equal to 0, that's the stable equilibrium point, and theta is equal to pi is the unstable equilibrium point. And we're going to look at, for Mathieu's equation, you'll notice the plus and minus here. Plus is for the stable case, minus is for the unstable case without forcing. And then we're going to look at the effect of the forcing, which is actually right here. So let me walk through these parameters. G is acceleration due to gravity. L is the length of the pendulum, which you see here and here. A is the amplitude of the forcing, and omega is the frequency of the forcing. So given all those parameters, we can then solve this single differential equation. Now, first thing you'll notice is it linear? Yes. Even though this looks complicated, it's linear in U. So it's a linear differential equation. We're going to see some really weird behavior, but it's not because it's nonlinear. It's actually a linear equation. Is it an ODE or PD? Well, you see ordinary derivatives, so it's an ordinary differential equation. There's only one independent variable, time, in this case. Is it linear? I already asked that. Is it ODE, PD? Well, it's an ODE. What was the other thing I'm missing? Oh yeah, boundary value, initial value problem. So it's an initial value problem. We're going to start with t is equal to 0 and then see how it evolves in time. Okay, so for a given volume, pendulum length L and acceleration due to gravity, so pick the planet that you're on, we're going to vary the amplitude and the frequency of the forcing. So the same pendulum, L and M, actually doesn't come in. You'll notice there is no M in Mathieu's equation. So the mass at the end of the pendulum does not affect its stability, which is kind of interesting. And then so again, we're going to look at the amplitude and frequency of the forcing and see how that changes what you would expect for a non-forced pendulum, or what you intuitively know is the case for a non-forced pendulum. So I'm going to use the same initial condition for all these cases. So U at t is equal to 0 will be 1, that's the position, and U dot at t is equal to 0 will be 0, that is the velocity. So 0 velocity and a position of 1. So essentially, we're going to take our pendulum and we're going to move it to a particular position which corresponds to 1, and just let it go, and then it goes back and forth. The A over L is going to be 0.01, so that's the ratio of the amplitude of vibration oscillation to the length of the pendulum, so it's 1%. So the amplitude of the forcing is only 1% of the length of the pendulum, so it's just a small bit of forcing. And then we're going to look at, for fixed G and A, which we just described, how does the frequency affect the solution. Okay, so here's a case with G over L omega squared is 0.24. So remember, if you go back to the equation, that's this coefficient right here. So G over L omega squared, we're going to set that to 0.24, and you get the solution. So this is U as a function of time. And you can see it oscillates back and forth, and the amplitude of oscillation, which starts at 1, so it started right there, and then it oscillates back and forth, 0 being the equilibrium position straight down, and you can see it oscillates with an amplitude which is bounded. Now the amplitude changes, we call this a modulation, but it remains bounded. It never gets bigger than 1. So we say that the solution is stable. There's no friction in this system, so it will go on like this forever. Okay, so that's a relatively linear type of behavior. So again, it's stable, as you'd expect for a pendulum hanging straight down. There is this modulation, which is caused by the forcing of the pivot point, but it's a stable solution. That's for 0.24. For 0.25, everything else is exactly the same, so I'm just changing the frequency of oscillation just a tiny little bit so that this ratio was 0.25, and now the situation is completely different. So we start at 1, but as time goes on, the amplitude of the vibration grows and becomes unbounded, and it's clearly unstable. And that's just, again, small change in the frequency, 0.25. Here's what happens when you go to 0.26. And you say, well, that looks familiar. Now, instead of going down and then up, it goes up and then down. But nevertheless, we have a modulated frequency on top of the regular frequency oscillation amplitude, but nevertheless it remains stable. So clearly there's something strange happening between 0.24 and 0.26. 0.24 and 0.26 are very nearly the same behavior in terms of stability, whereas 0.25 is actually unstable. So let's talk about that a little bit. It appears that the forcing within this narrow range of frequencies can produce unstable behavior. So again, that's just, everything's the same. I just changed the frequency of oscillation just a little bit, and it goes from being stable to being unstable to being stable again, just with this tiny little change. And now your first thought might be, oh, well, maybe the 0.25 is some sort of resonance, right? Because we know that if we force things at the natural frequency of the system, you can get a resonance effect and things can grow rapidly, but that's not what this is. So I'm not forcing at the natural frequency of the pendulum. And again, it's a linear equation, so it's not because of nonlinear effects. Now it turns out that there's an infinity of these, what we call unstable tongues. So there's a range of parameter, a tongue, a narrow range of omegas, for which we get this unstable behavior. So it's stable, then unstable, then stable. And it turns out there's an infinity of these. You can prove this mathematically, and you can illustrate it numerically, as we just did, that when G over L omega squared is equal to n squared over 4, where n is an integer, you will get one of these narrow tongues of instability. So again, there's actually an infinity of these. The one that we looked at was when n was equal to 1, and so therefore it's a quarter. But there's one at 0, 1, 2, 3, 4, all the way up to infinity, which is kind of unusual. Now, even more interesting, so this is a pendulum hanging straight down with the forcing and different frequencies of forcing, and you can make them go unstable. So you can make a normally stable system unstable with this forcing. That's not a stretch to imagine that that could be the case. However, now let's look at a situation where theta is equal to pi, and u is going to be measured from there. So now u is equal to 0 corresponds to sticking straight up. Theta is equal to pi. And so again, normally without any forcing, that would be unstable. And it turns out that with just the right amount of forcing, I'll show you one example, with just the right amount of forcing, you can actually keep it sticking straight up. So here's the solution for u as a function of time. For a over L is minus 0.1, so the minus sign now means it is straight up, and g over L omega squared is minus 0.001. So this is not the only value for which this works, but it's a fairly narrow range of values. And what's actually happening is, if you have a little disturbance, so your pendulum sticking straight up, if it starts to fall off to one side, the forcing brings it back. It falls off to the other side, the forcing tends to bring it back. Now that's a little bit more unusual. Again, it's not a nonlinear effect because it's a linear equation, and so there's nothing weird going on here. It's just that you can actually show, you can do an experiment. People talk, there's the broomstick experiment where you hold it up straight up. Normally there people are oscillating it back and forth, which makes sense. If it starts going one way or the other, you move the pivot point to get under it. Here, we're not doing that. Here it's oscillating up and down, and by doing so we can attenuate the unstable behavior. Okay, the next video we'll look at the Differential equation, and this is a very, very interesting nonlinear